Yeah, welcome. My name is Jens Dietrich, and I'm giving the talk for the paper on the recall of static Callgraph construction in practice that is joint work with Lee Sui, Amjad Tahir, and George Fortunas. So the paper is about problems in static Callgraph constructions. That is a static analysis technique that has been around for quite a while. We investigate this for Java, or Java bytecode to be more precise. And the problem is that if you have a Java program, like the very simple one in the box here, where a method invokes another method, then you try to model this as a directed graph, where the vertices are methods and the edges are invocations. And that has been around for a long time, so people have been researching this in great detail, and the problems or the challenges researchers have to deal with are precision to deal with false positives due to devirtualization, for instance. Scalability, there are even some theoretical limitations to how scalable you can make this in terms of algorithmic complexity. And the problem we are concerned with, we research in this particular paper, is recall. So that's how to deal with false negatives, with things the analysis misses, and that has attracted more attention since publication of the Soundiness Manifesto in 2015. So the problem here is that in languages such as Java, you have dynamic language features like reflection. So in the code snippet we see here, we have a method we invoke. So the method is a reflective object that represents some method in the code. And now that method is typically instantiated with some strings. And now the static analysis has to reason about this and make a decision which method is actually being invoked. And that causes some obvious challenges. And reflection is not the only feature like this. You also have dynamic proxies, invoke dynamic class loading, unsafe, native calls, and so on. So there are quite a few of those dynamic language features which have been cataloged and studied before. So from a very abstract point of view, we try in a static or dynamic program analysis to capture possible program behavior. So possible program behavior is here as a Venn diagram modeled as the methods we can reach during execution. So that is really what Callgraph analysis is mainly concerned about. And then we can run a dynamic analysis that gives us known program behavior. And the easiest way to do this is, of course, to run test cases. And the static analysis usually over-approximates actual program behavior, but it also misses things due to the dynamic language features, as I said before. And so we are mainly interested in studying this space here where we know program behavior exists, so we can reach methods if you observe actual program executions. But the static analysis doesn't really capture this. And the one core metric we are concerned about is the ratio between this area of the dynamic of known program behavior covered by the static analysis and the entire known program behavior. And that is the ratio we call recall. So as a methodology, we have a dynamic and a static analysis. We basically diff and compare them. For the dynamic analysis, we run tests, and not only tests provided by the engineers, but also generated synthesized tests. And as a test generation tool, we use Aerosuite here. We aim for high coverage to get as many methods reachable into our model as possible. There are a lot of technical details here, which you can look up in the papers. There's a long discussion on this. So we have to unreflect the tests, we have to instrument the code, and so on. But basically, after we have done this, we record the full context call trees. On the static side, we use Dupe as a static analysis framework because it contains implementations of most mainstream Callgraph construction algorithms, and it also has support for modeling reflection. And we use different precision soundness settings and modelings of third-party libraries used by applications. So the data set used is a subset of the xcorpus. So that is a set of executable programs that has been used in related studies. And we have 31 programs with generated and built-in tests. And when I make this claim, they are high coverage. Some coverage data, branch coverage data are below in this chart, and you can see different coverage charts for built-in, generated, and combined tests. What's really interesting here is that if you combine generated and built-in tests, coverage goes up, which shows some sort of orthogonality. And that in itself is probably an interesting finding. So research question 1 then was, how much does static analysis miss? And the answer is about 12%. So that's of course statistically across the data. So that is the median as seen in this chart. The static analysis used here is what we call the base analysis. So it's context insensitive and has no reflection support switched on. So then we move to a more precise analysis by switching on Callgraph sensitivity. And so the idea was that if you reduce the false positives, we might increase the false negatives as we are accidentally covered by the false positives, but we observe almost none of this across the data set. So there's a certain level of orthogonality between features that aim to improve precision and features that aim to improve soundness. Is reflection support effective? So we switched on reflection support, which was state of the art at the time. There has been development since we have done this, and that roughly halves the number of false negatives. So the answer is yes. However, it comes at a hefty price. So we set the timeout for the static analysis to 6 hours, and only for 20 of the 31 programs the analysis finished within the timeout. So the statement here is across the reduced data set of 20 programs. Then, and that's probably the biggest chunk in the paper, we analyzed the sources of false negatives, and we did this with a couple of patterns and a technique we called CCT tagging combined with a dominator analysis. So I explain the simplest pattern here, and the simplest pattern is reflection. So the idea is we have our context call trees over here, and then from the static analysis we know what the false negatives are. So what's the static analysis? We compare this with misses. Then we tag methods such as method invoke, reflection, if we see it in the graph, and then we use a dominator analysis by just removing those branches, and we see how many of the static analysis false negatives are removed by doing this. And that really means that method invoke appears on the stack earlier, so that is a possible explanation that the static analysis cannot really make it past this point and reach M5 and flags it as a false negative. So there are more patterns like this. Some of them are more complicated when it comes to dynamic allocation, and we have a couple of tags defined for them, and roughly they fall into 4 categories. Dynamic invocations, that is method invoke, but also stuff like invocation handler invoke, dynamic proxies, and we have dynamic allocations. It's something like class new instance, dynamic access, field get, and a system category that covers methods without call sites and method called from system threads. So doing an analysis shows some interesting results because dynamic invocations or method invoke, for instance, only explains less than 10%, typically statistically again, of the false negatives, whereas dynamic allocation and system are the main culprits that can explain most false negatives. The other category is what we couldn't really categorize with this pattern analysis. For this we did sampling analysis, and we basically found that it's the same patterns, but it's more kind of nested appearances of those patterns. An example for this are what we call double reflective factories that can explain most in this category. Yeah, coming to the conclusion, so the results can direct future research. If you improve the soundness of your analysis, where can you focus on in order to have the maximum impact? Hybrid analysis is beneficial, of course, if you use something like TummyFlex. You have a dynamic pre-analysis, and then, of course, you can kind of combine the coverage of those two, and you have an immediate benefit. And we have some interesting characterization of generated tests, how they can contribute to improve coverage or improve recalls. However, there are certain limitations, and they are not as good as built-in tests. And again, I have to refer to the paper for details. So that brings me to the conclusion. Thank you for your attention. I would like to acknowledge the project sponsors, which is the National Science Challenge of New Zealand and Oracle Labs. Thank you again for your attention.